Hi folks, and welcome to Maths and Physics for You. Today we're going to continue from last video. Last video we started preparation and revision for final exam Calculus 2, and we did an example on Green's theorem. Here also we continue with another example that uses Green's theorem to find the area of an ellipse. So to use this theorem to find the area of an ellipse, what we have to do work in reverse. So we have to use Green's theorem in reverse, and as we can see here in the last video, the Green's theory was in this direction, from right to left. Like if you have a force, a field vector F, which is defined as Fp I plus Qj, where P and Q are functions of x and y, and dr can be written in terms of its component dxi plus dyj. So this means that fdr we get dot product, so that will be p dx plus q dy, as we can see here. That's in this direction, Green's theory. And this is a line integral over C, over the line C or the curve C, and it's equals to the double integration. It's equal to the double integration along the region which is enclosed by the curve C. In this case, like we are trying to find the area of the ellipse, the region is the ellipse, and C is the boundary of the ellipse. And we saw what were the conditions that needs to be satisfied. So the curve needs to be closed and simple and positively oriented. That is, it's positive in counterclockwise direction. So that was like Green's theory. Now in reverse, so that we can find the area. So if we look at this, there is dA in it, the double integration. There is dA. So there is a special case when all these inside the brackets equals to 1, we get a double integration 1 dA. So the area of the ellipse or any closed shape is given by the double integration of dA, 1 dA. So all what we have to do here is transform the double integration to line integration, and that will make it simpler. So we choose this to be equals to 1, as we see here, dq dx minus dp dy equals to 1. There are many possibilities to do that, but the simplest one I found is by choosing q equals to 0 and p equals to minus y. You can check that it satisfies this one, and it does, because that will be 0, and minus 1 will give you plus 1. So that's satisfied. Very good. So we use this to sub it in the line integral. That's how we want to find the area, from here into this. And we can see it here. So it's again written. So A equals to double integration dA. It's the line integral now, p dx plus q dy from here. And here we sub these values which we chose. Q is 0, so that cross out. We are left with p dx, and p is minus y. So that's minus y. It goes there. And the easiest way to do the integration for a line integral in this case is to use parametric equations for the ellipse, which is in this case x equals a cosine theta, y equals b sine theta, and dx is minus a sine theta d theta. We sub this in this formula here, as we can see. So writing it here, that's minus y minus b sine theta, and dx is minus a sine theta d theta, and we integrate from 0 to 2 pi as it is for around the ellipse in the positive direction. Simple substitution, folks, and that will give you ab sine square theta d theta. As you know from trigonometric identities, which you learned before, sine square theta can be changed into 1 minus cos 2 theta divided by 2, So we have this d theta. This is easier to integrate. So you got AB over 2. Integration is simple here. So you got theta minus 1 over 2 because we have 2 theta, sine 2 theta. Simple substitution of 0 and 2 pi, as you know, that will give you AB over 2. Simple substitution, and you get pi AB. So that's what we get. The area of the ellipse, as you know, is A equals pi AB. And there you have it, folks. Thank you for watching, and please subscribe, and see you in the next video.